In this talk, we are going to focus on a set of cognitive architectures developed for the iCub robot, also for other robots like the Pepper. And we are going to cover different aspects of cognitive modeling. We start from language learning, and then we look at abstract knowledge and abstract words, and then we finish towards more social cognitive skills. So let's start from the consideration. Our approach is called developmental robotics because we want to model in a robot the developmental stages that, for example, a child goes through when she has to learn language or when she has to develop social skills. So let's consider the example of language as a prototypical example, and also because this is part of my research. So if you consider language and technical solutions, robotics or AI solutions like Alexa to language, you can in principle pre-program a system to use to have a dialogue, let's say in English, when we use Alexa, Siri, or other these systems. But this is not the same case in robots, because if we want a robot to understand language and have a dialogue with us, we will like the robot also to be able to understand the meaning of words, meaning grounding the meaning of words in action or in perception in this specific case. So this is hard to do. How can we address this problem? In developmental robotics, we say that you could design architectures, cognitive architectures inspired by phenomena, mechanism, principles in child psychology. So let's look at some of these principles. For example, children are slow, although later very efficient, something called vocabulary spurt, sudden increase of the lexicon. But at the beginning, they are very, very slow at learning language. So maybe pre-programming a robot with the full Alexa-like knowledge of the whole English dictionary and grammar might not be a good idea. Then children use their body for situated interaction and for learning, right? You will see in the video here that it's very important in some way to consider aspects related to social gaze, to pointing, but also to object use. So we try to model these kind of embodiment strategies, body-centered strategies in our robot models, and robots, of course, are suitable for this. When you look at multimodal integration from a language point of view, language is grounded and therefore is multimodal because of the perceptual and motor component, but also internal emotional components, if you want. Even if you have a brain-like architecture, which is modular, that does vision in one element, in one module, in one part of the cortex, motor in another part of the cortex. In reality, we know, studies from Puvel Muller's, for example, that in reality, really, what happens is that motor areas are also engaged in syntactic tasks, but also engaged in representation of the word meanings and so on. So integration of the multimodalities, it's very important. And then, of course, it's as important as the rest, social learning, children learning in a social context. So for example, in embedding some kind of theory of mind to allow the robot to predict the intentions and the goals of the others will facilitate the interaction, including the learning interaction. So this is the context from which we start, and we initiate our presentation with the first architecture we developed a few years ago as part of the iTalk project, and then the Poeticon++ project. It's called the ERA architecture, epigenetic robotics architecture, applied to many different aspects of language learning. So this is not a general cognitive architecture that's meant to model all aspects of cognition, but it's really focused on grounding language via action and perception. The architecture is based on a series of pre-trained networks, let's say coordinate maps, that allow you to have a topographic representation of color categories and similarities, shape similarity for object classification, and then body representation, because body plays a role. In speech, we use localist, one-hot encoding type representation, but you could also have a some-like representation similarity, let's say, in the acoustic space. Then we add other elements related to memory, representation, and time-based representations. It could be an eco-state network, or we have used the Hellman networks, for example. And then, of course, a series of routines to do attention from the point of view of the robot, and then pointing and so on. The way we approach this, the validation of the architecture, is by reading papers in child psychology, but more importantly, by collaborating closely and directly with many baby labs. We start with Linda Smith in Indiana and other researchers linked to the same school in developmental psychology, so Jessica Horst and Katie Toomey. Katie Toomey is now my colleague in Manchester. Then we have worked also with the baby lab in Plymouth, led by Caroline Flocha, and also new collaboration with Milan Cattolica. There is a theory of mind and social cognition group in developmental psychology, Antonella Marchetti and colleagues. And we map this time scale of cognition, first year phonetic discrimination, second year perceptual and early vocabulary learning or vocabulary spurt. Vocabulary spurt, when you have a sudden increase of the size of the vocabulary, you just learn a word at a time through a mechanism called fast mapping. And then we have language production, complexity, grammar, and so on. So let's look at the demonstration first, and then we look at some numerical results. And I'm going to explain the multiple child psychology mechanisms that we have implemented using the same architecture. So this is called fast mapping. I see, I hear, associate sound and vision. And we are testing the robot knowledge via social cues like pointing.
Where is the statement?
So this is called mutual exclusivity. If I see a new object and I hear a new word, by mutual exclusivity as a child, I know the word is the name for the new object. Of course, you need to make sure you don't forget things. Now, what order? Two words together in a sequence.
Look at the red cup.
Let's say adjective and noun.
What is
The
this?
robot has a recurrent component, the architecture, that the robot uses to repeat words in a sequence.
What is this?
And now we do generalization of the only word I know for is the shape, it's not the color, right? Here I know the color,
What is this?
the primary color.
Red.
I don't know the shape. But now we learn two new concepts,
Look at the green
a new
leaf.
color, adjective, a new noun. And now we do mutual exclusivity using color. But we learn two words in one go.
Where is the purple carton?
So I know green, mutual exclusivity, the other one is purple. And of course,
Where is the green carton?
I know green and I know carton. So that's the way you can combine together many mechanisms. Remember, we like to collaborate with child psychologists, not only to learn from them, but to give something back. In fact, in a study with Linda Smith and other colleagues, we ran a series of experiments. And the last two experiments here on the right were studies where we predicted the performance of the child that was verified in a later experiment in terms of use of embodiment skills. Here we demonstrate that if you use 2 dimensions or organization of space and posture in the experiments, in Linda Smith's original studies, they manipulated left and right. We also manipulate vertical dimensions. We predicted that in some condition, when you move the objects to the opposite side of the learning space, if you also change the vertical posture, then you get a above chance performance, which means the child or the robot is increasing its lexicon by using these additional strategies. So it's a two-way collaboration between us and psychologists. Now let's look at a slightly different developmental architecture, still for language, but we are looking at abstract language, including abstract knowledge referring to numbers, for example. So in a previous study with Alessandro Di Nuovo, we showed that the robot doing finger counting can be trained to perform simple operations. And if here we visualize the structure of the representation of numbers, when the robot is doing at the same time finger movement and number repetition, 1, 2, 3, 4, you get here a hierarchical organization of the similarity of the internal layer. This is the intermediate layer of the network, which is very closely related to numbers. 1 and 2 are close to each other, 1 and 10 are very far. If instead you teach the robot without using its body, only to repeat, to do a recital of 1, 2, 3, 4, 5, the similarity here are more about sounds than numbers. So 7 and 6 or 2 and 10 are closer to each other because you have sound similarities, right? 2, 2, 2, 10, 6, 7, rather than 1 and 2, sorry, 2 and 10 being in the other chart here on the left, very different because 2 and 10 are numerically very different, and your body, meaning your fingers, allow you to understand this implicitly, this representation. Very recently, this is a paper being published this year. My student, Leszek Pecina, in collaboration again with Alessandro, we did a study where we replicated 3 conditions in Alibali and Di Russo child psychology studies. You see how children can learn, and in our case, the iCub robot, by pointing, by no pointing, worse performance, pointing, better performance. But also you could have a puppet that points in the experiments, and in our case, you can have the iCub that follows a puppet that points rather than the iCub performing its own pointing gestures, count in this case to count. And this was implemented using partially a convolutional neural network and a recurrent, of course, architecture in a real world. So we collected data from the iCub, we did some data augmentation, manipulation to increase the data set. And you can see the iCub counting there. And finally, the other architecture is more of a social cognition architecture. In particular, we focus on trust, the relation between trust and theory of mind. Theory of mind is the capability to know that the other person has certain mental states, meaning certain goals, certain beliefs. And therefore, if you link this to trust, I can believe that the intention of the others are positive towards me, trustworthy, or they can be negative. Here we model the robot's own artificial theory of mind. The way we do this, instead of using neural network, we use Bayesian networks, and we train our Bayesian network to fine-tune the probability dependence between the different states using these Bayesian algorithms. So basically, a child, to perform an action, must integrate its own belief about the world and the action that the person performs on the world and the belief that the person uses to perform the action, which then is integrated with our own belief. And I'll show you how we do this. This is the Pepper robot. It's an experiment based on a task called the Sally-Ann task, collaboration with Antonio Chella in Palermo. So let's stop here. You see there is a task that assesses the level of development of theory of mind capabilities in children. You show this cartoon in sequence. There is Sally, there is Anne. Sally hides the object in the left basket. She goes away. The naughty Anne changes the location of the object when Sally is away. Then when Sally returns, you ask the child, where is Sally going to look for the toy? Children, after 6, 7 years of age, have a theory of mind representation. They know that Sally doesn't know that Anne swapped the object because Sally was away. So they know that Sally, they say, well, Sally will be looking for the object here on the left. Instead, if you are younger, you have no theory of mind, and the children say Sally is going to look for the object in the box because this is where they last saw it. Okay, this is a classic example. Vanderbilt actually changed the setup. She used stickers, more active representation instead of the passive scene. This is what we replicated in the study. There are 3 stages. First, you familiarize. You start to build an updated theory of mind of your person. So you identify the face. So this trigger label is for us in the video. The robot doesn't know it. The robot is building its own Bayesian network to predict the behavior of the person, integrating so another person, a helper in this case. Remember, the robot predicts the location of the object, observing the object, and knowing later the typical belief and social trustworthy behavior of the person.
Right.
So this is the estimation stage. Here is why the networks allow you to predict the position on the left to integrating the two bits of information.
I've never seen you before. I'll call you Informer 2.
So you can then use existing theory of mind from other people in your group to map this into 2 new people.
Hello again, Informer 1. I know the sticker is on the left. I also believe you would point left to me.
So what we demonstrate here in the final element is called, if you want, explainable AI. The robot explains to the person its own decision-making process. And we know, again, if you link this to trust, you trust more, you trust people better if you can ask them, especially when they make mistakes. So a new line of research looks at trust, theory of mind, and explainable AI. So let me summarize this short presentation with a take-home message. What are the positive aspects of our research and the achievements? We show that embodiment is very important in various aspects of development, not only language, but also in social cognition and, for example, in abstract knowledge like number count. We used the same architecture for multiple phenomena, if you remember the first video on the language grounding. In some cases, we can do a very nice match with empirical data from child psychology, including predicting what children will do in a future experiment. And we integrate linguistic skills or abstract knowledge skills with social cognition. We have experiments where the robot uses the theory of mind to decide whom to learn a word from. In the sense, if you have a bad teacher and untrustworthy teacher, you wouldn't update your representation of the lexicon. Future, where are we going from here? We would like to model a scenario where you have open-ended, continuous scaling up of the repertoire of our agents. And you will see also in the final consideration here, part of the discussion is, are we moving towards a general integrated cognitive architecture, or are we integrating architectures? Not necessarily having general architecture, let's say like a SOAR architecture or ACTAR architecture. So our approach is to integrate smaller components. That's why in the first video that you saw, we combine a recurrent connection from another study with an element of this architecture we call Cognitive Robotics architecture. And then remember the final consideration was the importance for trustworthy robots to consider theory of mind and aspects of explainable AI. Thank you.